Okay, so good morning and welcome to Classical Mechanics 1. I hope those who are here can hear me.
Yes, sir. Yes, sir.
Oh, okay, very good. So I'm glad you have joined a few minutes in advance. So this is our second lecture meeting of this course. Today is the 4th of August, Thursday, 2022. So while we start, or before we start, are there any I had a couple of things to mention. Yeah, one is that the video as well as notes from the last meeting have been posted on our course website. So this information is contained in the email I sent out, as well as written over here on the screen. I can give the rest of the address for this website. Any questions about one moment? Yeah, one moment. Yes, so okay. So I'm just starting the class. So I have to, I'm on the thing. So can you come this afternoon? Yeah, you came if you were left. No, I was here the whole afternoon. I might have got. Anyway, I'm glad you have come. Because I have to teach now. Yeah. So can you come?
We come at 2 after right after lunch.
After lunch, yeah. Just leave. Okay. Yeah. Yeah, I had to go to the door to it. Yeah. Yeah. So okay, while we wait, are there any questions? Okay. I know there has been a request to conduct the class in hybrid mode. I am looking into this. Okay, so there was a question about textbooks which you may consult. So let me suggest some. I will put the details on the website as well. Yeah, so there are many good books. The viewpoint we will take is not specifically from one textbook. I mean, it is adapted to what I feel would be appropriate, and based on the background of students. So one book is by Klepner. Klepner and Kolenkov. Introduction to Mechanics, Cambridge University Press. There's another one by Kittel, Kittel, Knight, Ruderman. That's also, I mean, it's called mechanics, I think.
Sir, I think the screen is frozen.
Okay. Sorry about that. Are you able to see the screen now?
Yes, sir. Yes, sir.
Okay. So as I was saying, there's a book by Klepner and Kolenkov, Introduction to Mechanics. Mechanics, and that's a nice book. So is the one by Kittel, Knight, Ruderman, and Ruderman. That is in the I think it's the Berkeley physics series, volume 1. There are others. There's one by AP French. Yeah, I'm trying to remember the name. Yeah, I think it's something like MIT Introduction to Mechanics, if I'm to guess, right? Yeah, I can't.
Sir, I think it's Newtonian Mechanics by AP French, MIT.
Okay, so it's Newtonian Mechanics. So is that Dhriti Maya Sahu who has told me?
Yes,
that?
sir. Yes.
Okay, great. Newtonian Mechanics. You said something like that, right? Newtonian Mechanics, MIT.
Yeah.
Okay, great. Yeah, yeah. I think that may be McGraw-Hill. I forget. Yeah.
Sir,
Yes. Yes. Go ahead.
no, nothing.
Okay. Anha Chaturvedi asked me whether I can
yeah.
conduct this class offline. Yeah, it can't be completely offline because nearly 50 students are not here. I am looking into doing it in a hybrid fashion. I will get back to you on that. I'm aware of this request. Are you here at CMI?
Yes, I'm here at CMI.
Okay, so yeah, we'll be in touch. I will let you know about this.
Well, yes, I was wondering if Arnold's book on mechanics will be accessible to us, classical mechanics.
Which one? The one by Arnold, is it? Is that the one you said?
Yes.
No, I mean these Arnold's book is is a more of a mathematical introduction to the subject. I wouldn't suggest that as a first place to read this. I think one requires. I mean, you're welcome to look at it if you want, but it is not very accessible at this level. And the course that I am teaching is not geared towards that. So I would definitely recommend you get your intuition and basics elsewhere. And one can always look at that at a later stage. Yeah, there are many other books. I mean, and they vary in their emphasis. Some have more of the experimental basis, some have more formalism, some have more mathematics, as Arnold's does. Yeah, it's quite important to get the physical intuition as well. Okay, and some of the details. Arnold's book is rather terse, so yeah. There are others. I will make a list and include it on the website. But I've mentioned these 3 for now. They're all. I'm not specifically following any one of these, but they are all available. I think there's one by David Morin. Yeah, so that is yet another one. So they're all available in reasonably priced Indian editions. Okay, any other question right away? All right. If not, let me go back to our discussion from last time. If you remember where we were, we had introduced the concept of vectors and introduced the dot product of a pair of vectors. We had also the notion of a length of a vector and now the angle between a pair of vectors. yeah, that was this formula for the angle theta is the arc cosine of A dot B upon A times B. Then we went on to talk about the component of a vector in the direction of another vector. So this was the component of B in the direction of A. And that was defined as the dot product divided by the length of A. So that is, in other words, simply B dot A hat. Yeah. All right. And as we said last time, this is not a vector. This is just a real number, but it can be positive as well as negative. Yeah. Yeah. Okay. Yeah. Yeah. So the and it doesn't depend on the length of A. It depends only on the direction of A. Now there is, as well, somebody asked at the end of last lecture, there is also a related vector which you can define. This is called the projection. So I will write it P A hat of B. So you have a vector B, you can project it along A. It's called the orthogonal projection. And that is a vector defined as the component of B in the direction of A times A hat. So we've now defined a vector. Geometrically, it is okay. It is called the orthogonal projection of B on A, and pictorially it is given here. It's the construction we discussed last time. We have a vector B, we have a vector A, we have the associated unit vector A hat. Now you drop a perpendicular from B to the vector A. It meets at some point. The resulting vector from the origin is called the projection. So that is P A hat of B. Yeah, so it has a coefficient which is given by the component of B in direction of A. Yeah, so one can of course play this game in the other direction. Yeah, so this can be played in the other direction. One can talk about the component of B in the direction of A as similarly the component of A in the direction of B. These are different quantities, of course. So this A dot B hat is the component of A in the direction of B. And both are useful concepts. You can draw a similar picture to visualize that. Any question about this concept of a orthogonal projection? Okay. Yeah, so we already last time talked about the norm of a vector. I just want to repeat that the norm of a vector is the same as what we call the length. But as a matter of notation, sometimes we put two lines, two vertical lines on either side when we use the name norm. It really doesn't matter here. You can use one line, not so specific. And it is defined as the square root of the dot product of the vector with itself. Yeah, and it's a non-negative quantity. Yeah, so the zero vector is the only one with zero norm. Okay, so the norm we are working with is called the Euclidean norm. Okay, so this is the standard one that we have a good intuition for. Yeah, Euclidean length or norm. Okay. Now, an important example of a dot product appearing in mechanics is the work done by a force. Okay, so the work done by a force on a particle can be regarded as a scalar product, as a dot product. So suppose a force, I'm going to say this a little bit imprecisely, but let us do it first. Suppose a constant force, yeah, so a constant force acts on a particle, and displaces it by a displacement vector S. So that is in this picture, the particle started out at A, where its position vector from the chosen origin was A. This is the chosen origin. A force was applied to it and it moved to B. So this is its final position vector. Now its displacement, the displacement is again a vector. It is defined as B minus A, the final location, final minus the initial. And that I have given the name S. Notice that S is a vector that does not emanate from the chosen origin. It emanates from the initial location. So it's a vector of a different sort. Now this force F I have indicated in some direction, and we will declare that the work done is F dot S. Okay, so the force vector dotted with the S vector. All right. I've been a little bit casual in this statement. I would like to refine it a little bit, but any question so far?
Yeah, I had a question about the previous point, that the
Yes.
norm of a vector could be written as the dot product, the root of the dot product of the same vector with itself. So is that an accident? Like for given any norm, so there can be multiple norms, right? So given any norm, could we express it as, we could be create a dot product, so such that we could express it like that?
Okay, no, this is a good question. I'm not sure I'm going to answer it fully here, but
Allow me to satisfy the parallelogram law.
wait, there is some echo from somebody.
Yeah, so like the norm is to satisfy a certain parallelogram law, like norm of A plus B plus norm of square plus norm of A minus B square is 2 times norm of A square plus 2 times norm of B square. Like if that law is satisfied, then
Yeah, so okay, I mean, there are several people saying things. I'm not sure if the person who asked the question and the second person who spoke are the same. Yeah, so I am here, let's be very specific. We are talking here about the Euclidean dot product, and from that I have defined a norm. Now you are not obliged to do that. The concept of a dot product is more general, as is the concept of a norm. Now it's an interesting question whether every norm arises from a dot product or not. I don't wish to address that question here. One has to look at it carefully, separately. But in principle, they are distinct notions. It is in this case that the norm is given by the square root of a dot product. And in many interesting cases that we will encounter, that is indeed the case.
What is the dot product?
The dot product for me, see, we are building this thing not really axiomatically, but through the kind of examples that we need. So I have defined the dot product. You may argue that I have been somewhat circular in my arguments or definitions.
That's what my problem is actually, because
No, so let me be clear. I have talked only about our space of interest, which is three-dimensional Euclidean space or the plane. And when we have a vector, we think of it as a rigid arrow. And I said that its length is the length measured by a ruling stick. Now, so that already has defined a length. Or a norm. You could ask what properties this norm has, and that is an interesting question. I don't wish to discuss that in detail here. We have separately defined an inner product using this notion of length and another notion of angle, which is already available to us from our human experience. Yeah, I have simply defined the dot product as a b cosine theta. Okay, so yeah. But this is how the subject developed. I have to emphasize, this is how the subject developed. You already have some notion of length, which you may want to call a norm, fine. You already have some notion of angles, which you measure using your devices, and you define this dot product that way. And then you notice that the angle can be expressed in terms of the dot product. Yeah. And the length also can be expressed in terms of the dot product. And so you conclude then that maybe even if you did not start out with a notion of a length and notion of angles, you could construct such notions if somebody provided you an inner product. Okay, so we reverse the procedure. So then the inner product becomes more fundamental, and somebody gives you an inner product, and from that you can construct lengths and angles. Okay, so yeah, there are interesting questions about what additional properties this norm satisfies, like triangle inequality and so on. Yeah, I think that is best addressed elsewhere. Yeah. So who asked about this?
I'm unheard.
Anhat Chaturvedi. Okay, okay. Yeah, I'm not sure I have addressed your question completely, but could you say if you want to know something specifically right now?
No, that was my only question, because I wanted to know if there was a purpose behind defining it that way and is it useful, etc.
Yeah, you have used very good words. Yeah, the process of is it useful is a very good question, and that is plays an important role in our discussion here. And the order of operations is also very important. Yeah, here we are looking at nature using our tools and defining certain quantities, and then defining the mathematical notions associated to them. And then afterwards, we reverse the whole process. We simply define some norm using some axioms and then go backwards. Yeah, but that backwards approach is not the way we start. That's not the way a mathematician starts either. So I want to do it in this manner, just for now. Okay. Now, in addition, we have another concept. So just to okay, yeah. So let me leave aside this. No, actually, I wanted to say something about work, which I forgot almost. An important thing about work is that I've been a bit casual here. Strictly speaking, we talk about the work done by a force, not for a finite displacement to begin with, but for an infinitesimal displacement. Yeah. So what I mean is that, and the force need not be constant. I mean, if you are pushing something with your muscles, after all, you're going to get tired. So your the force may not be the same at all times, but it is more helpful and meaningful to talk about the initial location of the particle. Yeah. So that is over here relative to some chosen origin. You apply a force, and over a very short instant of time, the particle moves somewhere. Yeah. So that is your final location B over an infinitesimal time. And in that, and that motion is caused by a force. The displacement that is suffered is called an infinitesimal displacement, ds. It is again a vector, but it's of infinitesimal length. It is B minus A once again. And we say that the work done, the infinitesimal work done, which I will write dw, is f dot ds. Okay, so this is the basic definition of the work done by a force due in an infinitesimal displacement. Yeah, and then of course, if there is you apply the force over an extended duration, you would have to combine these infinitesimal work done and get the total work done. So it is a little bit too simplistic to think that the force may be a constant, or even that it is not relevant to think about whether the particle went in a straight line or a curved path and so on. So those are all relevant issues. So to understand the work done, one really needs to go back to the infinitesimal work done and work one's way up. We will talk more about this later on. At this stage, I just want to give examples of vectors. And the infinitesimal work done is a scalar. It is not a vector. So, okay. Any questions so far?
Sir, how does a norm differ from the magnitude of a vector?
It does not differ. It is a synonym. Magnitude of vector, length of vector, norm of vector, all are same for our current purposes. Yeah.
Okay.
Yeah. So I don't wish to make any distinction among these concepts. It is just that you will hear different words in different places, and I want you to be aware of these words. And you will not be badly off to have all these words in your vocabulary. Okay. And the intuition should be that they are basically the same. Okay. Then I want to, so that was Sahil Lakmani, is it? Did I get your name correctly?
Yes, sir.
Okay. Yeah. I may not be able to pronounce your names properly, so I encourage you to please correct me, or to speak your name. That will make it easier for me. Or you write your name in some language which is phonetic, then I will understand. Okay, so now we go to another concept, which is vector or cross product. Another useful concept. So the vector or cross product takes a pair of vectors A and B, say, and produces another vector. And at this stage, we are going to define it simply as a vector whose magnitude is AB sine theta, where theta is the angle between the two vectors. Yeah, so I have a vector here A and another vector B. Yeah, so this is the angle theta, and for now we are simply saying that this is the magnitude of the cross product. So this is simply some number, and in fact it is a positive number because the sine of the angles between 0 and 180 degrees are all positive. So now if A pointed this way and B pointed that way, I will define this as my angle. All right. So I'm not going to define that as my angle. Yeah. So this is a positive quantity. Okay. Now, yeah. Now, being a vector, I have to also tell you which way it points, and that way is defined in a very human manner using our hands. So its direction is determined by the so-called right-hand thumb rule. So if the fingers of the right hand curl from A to B, then the cross product points in the direction of the thumb. Okay, so let's give an example. This is a nice rule to understand and know how to implement. So I have the fingers of my hand pointing this way, and then the thumb is pointing this way. As the fingers go from here to there, let me do it in the video. If this is the initial direction A, and this is the final direction B, then the thumb points in the direction of the cross product. So otherwise, if this is the direction of A and that's the direction of B, then thumb points the direction of the cross product.
Okay, I had a question. So direction meaning you could take it from either side, right? From A to B in the top and A to B. So which one?
You're quite right. So we have to be precise about that. We are talking about the cross product A cross B. And for that, you need to curl your fingers from A to B. Yeah. from A to B. If you're interested in B cross A, you must curl your fingers from B to A. And as you have noticed, the direction of the thumb will be the same or different? Please tell me.
Different.
Yeah, in general, it will be the opposite. Yeah. So A cross B points in a direction opposite to B cross A. Yeah. So you're quite right. So let us make a couple of comments here. You have rightly pointed out that the order does matter, very much so, unlike the irrelevance of the order in the case of the scalar product. Yeah. So in particular, A cross B points in a direction perpendicular to both A and B. We have people joining. Yeah. So that is clear from this demonstration. If you go from A to B, the thumb points perpendicular to both A and B. And furthermore, as has just been pointed out, A cross B is minus B cross A. Yeah, the magnitude doesn't change. The magnitude doesn't change because the magnitudes of A and B are the same, and the angle between the two vectors, I have simply called that to be an angle between 0 and pi. Yeah. So I'm taking my convention as this angle lies between 0 and pi. So the sign of that angle is always some positive number. But the direction gets reversed if you reverse the order in the cross product. So we say that it's antisymmetric. A specific, in particular, the cross product of a vector with itself is the zero vector. Okay, and that's because of several reasons. One is simply that the theta angle between the two is simply 0. And the other reason, if you use the thumb rule, is that A and A point in the same direction. So there is no clear way in which you can curl your fingers, right? So you could place your fingers along A in any one of infinitely many manners, and each one will give you a different direction of the thumb. So if you take this thumb rule really seriously, different people will arrive at different directions for the cross product. And then you will appeal to our discussion from yesterday or day before, where we said that the only vector that points in all directions, or a vector that points in more than one direction, is the zero vector. Okay? So A cross A is simply 0. So we say that the cross product is not commutative in general. A cross B in general is not B cross A. And the cross product as defined here is specific to 3 dimensions. We do have a cross product of vectors on the plane, but which way would they point? The cross product of 2 vectors on the plane. Can you say something about that?
Perpendicular to the plane?
Indeed. So the cross product would point in a direction perpendicular plane. That's quite useful. We will often regard the plane as embedded within 3-dimensional space and use that setting. Yeah. Okay. And last time, one of our friends told us that the cross product is, or asked about whether the cross product is generalized easily to other dimensions. There is no straightforward generalization, but if you want some properties to be preserved, there is the concept of a Lie algebra, and that does extend to other cases. Yeah, but that will not play a serious role over here. Okay. Whereas the dot product is fairly straightforwardly generalized to any dimension Rn, R2, R3, R4, anything. Okay, so let me now just remind you about this procedure to compute the direction of the dot product, the cross product, and a little notation that one uses. So if A points this way and B points that way, then A cross B points out of the plane of this picture, out of the plane of the picture, and that circumstance is denoted by putting a circle with a dot. I mean, this is some peculiar convention, and that just means that the cross product points out of the plane. On the other hand, if you're considering B cross A, B is this way, A is that way, your right hand thumb rule will indicate to you that B cross A points into the plane, and that is indicated by this circle with a cross inside. So that says that B cross A points into the plane. Yeah, so some textbooks use this notation. You will not use it too much. Sometimes it's helpful. So for those of you who have not used this thumb rule before, I very much encourage you to try it out with some concrete vectors. I mean, like the vector from your nose to the corner of the room and some other vector, and figure out how the cross product points. There are other versions of the thumb rule. Some people use the screw rule. You are welcome to look that up. This, which will give you the same thing. Or right hand thumb rule. Yeah, so there are other ways to determine the direction of the cross product. Now let me come to an example of a cross product that plays an important role in mechanics. This is the torque vector, the torque due to a force on a particle located at the position vector r relative to a given origin. So you will notice that my sentence is rather long. That's for a reason. We have to, whenever we talk about the position vector of a particle, it's always relative to some origin. So this is something we have to keep in mind. And so, and the force, of course, acts on the particle at its instantaneous location. Okay, so that is how the force is a vector that emanates from the position of the particle, whereas the position vector emanates from the chosen origin. Yeah. Now, given these two ingredients, namely the position vector of the particle and the force that's acting on the particle, we can define a third concept, which is the torque, which I have denoted tau, vector tau is r cross f. So in the picture that I have drawn, please tell me whether the torque points into the plane or out of the plane.
Sir, into the plane.
Yeah, indeed, you're right. I think that was Srinish Shinde as well as perhaps others. Yeah, so indeed into the plane, because r cross f will suggest, using your thumb rule, the thumb points into the plane of the paper. Okay, so let me, of course, I have not told you what the physical meaning of torque is or what purpose it serves. Yeah, and we will do that. Right now, I'm just giving it as an example. Now, let me ask.
Actually, I didn't get that. Okay.
Okay, why does it point into the plane? Is that your question?
Yes.
Indeed, good question. So, okay, yeah, I think.
So you imagine the vector f point, starting from the origin.
Yes,
and
yes.
then, so my question is, so should you move from R to F in the left direction or R to F in the right direction?
Okay, you have caught me in my imprecision. You're right. I defined the cross product of two vectors with a common origin. Now R and F don't have a common origin. So what am I talking about? So first of all, I am suppressing the fact that I have parallel translated F to the location of the particle, sorry, to this origin, which I suppressed and didn't say. I hope you are willing to believe me that there's basically only one way to do this. Yeah, and having done that, we are looking at R cross F. So this is R and this is F. Yeah, and R cross F will go this way.
So what, in the previous example, it went towards the left from R to F, the other direction. So it's basically which is the smaller angle.
Okay. No, I'm not. Okay. You're saying it's this angle rather than some other angle. You mean this angle, is it?
No. The other angle from R to F. From R to F.
Okay. You mean this one? Is that the one you're looking at?
Yeah, this one.
Okay. Yeah, you're right. No. I mean, I hope you will agree with me that this vector is minus F rather than F.
Yeah. So
Um,
which one should we take?
Oh, you take F.
But
You parallel
oh wait,
transport.
no, not the reflex angle. If you go from R to F in the left direction, so basically R to F it's circular,
360
right?
minus theta.
Yeah, but
Yeah,
R
three-
to F already tells you which angle. You're saying from R to F.
Yes, but it doesn't, right? Because there are two angles. Now you can take either theta or 360 minus theta.
Ha ha ha. Okay, okay, that way. No. I have declared previously that we are not taking angles above pi. Uh,
So what if it's equal to pi?
Oh, that is a good question. That in that case, fortunately, the answer is very simple. Okay, tell me what happens if R and F. Okay, let's take your example. So suppose R is this way, and my force is pushing it this way, right?
Zero. Yeah, zero. I got it.
Okay, so in this case, you are suggesting to parallel transport F here to the common origin. And as you have rightly pointed out, the angle is 180 degrees and the sine of 180 degrees is 0. So the torque is 0. So it doesn't matter whether you choose this angle or that angle. Yeah. Okay. Yeah. Okay. I mean, here it didn't matter, but we tend to take the angle measured counterclockwise. When we say the angle from R to F, it is angle measured counterclockwise. Yeah, let me, we will play around with this more when the need arises. But
Sir,
no,
and
yes, please.
I have a doubt with regards to comparing dot product and cross product.
Who are you? Who are you, please?
Sir, my name is Kaustubh Manda.
Okay,
Um,
Manda, please go ahead.
yes, I had a doubt. I was wondering if we could compare dot product and cross product with respect to different reference frames. Like, when you change the reference frame, considering that both of them are stationary with respect to each other, the dot product remains the same. However, the cross product would differ.
Yeah,
Would
there is
that be
something.
correct?
I mean, you're on the right track indeed. See, to be honest, I have not yet talked about changing reference frames and so on. But let me very briefly say that the word scalar, the scalar product, is a scalar quantity. And in physics, a scalar quantity is one that does not change with a change of coordinate frame, yeah, or reference frame, as you said. On the hand, a quantity like a vector can depend on the frame of reference or the coordinate coordinate frame. So yes, you are on the right track. In that sense, a scalar product is independent of that choice. Is that roughly what you were asking?
Yes, sir.
Okay, good. Yeah, so vectors do transform non-trivially under certain operations, like rotations or a change of reference frame, whereas scalar quantities tend not to change under rotations. Yeah. So the angle between two vectors is unchanged even if you rotate your frame of reference. Yeah, it remains 45 degrees or 90 degrees as it used to be in the previous frame. Okay. Yeah. But we will talk about these things again in the coming days. So okay, I had a small question over here. How might a force point so that imparts no torque on the particle? Could you elaborate on this?
Sir, it must be in the direction of the displacement vector or opposite to the direction of displacement vector. So torque will be 0 in both the cases.
Yeah, you're on the right track. I just want to say that we have to use our words carefully. The torque doesn't depend on any displacement vector. So please revise your answer.
So position vector should be in the same or the opposite direction of force. And
Indeed.
secondly, the force should not be applied on the origin itself, in which case
Okay.
position itself is 0.
Okay, fine. Yeah. So the previous answer, which was almost right, I forget who spoke. Please tell me.
Sir, it was me. I can repeat it properly.
Yeah, no, but what's your name?
Srinish.
Srinish Shinde, was it?
Yes, sir.
Yeah, okay, great. Now you almost had it, just that I would replace the word displacement vector by position vector. That was the only change. And then somebody else elaborated. Was that
Sir Kaustav.
Kaustav Manda, right? Yeah.
Yes,
So you rightly pointed out that we should use the position vector in place of displacement vector. So the torque is basically is zero if the force is collinear with the position vector. And in fact, we already looked at an example over here where that is the case. So the force points opposite to the position vector. But even if the force was in the direction of the position vector, the torque would again be zero. Yeah. Okay. Of course, there are degenerate cases where the position vector itself is zero or there is no force. Yeah, those cases are also possible. Okay. Any question about this torque defined as a cross product? Yeah, I mean, what I think the first person Shinde said is not completely wrong. I mean, force does cause displacement, but the definition of torque at that instant is not dependent on the displacement.
Sir, what does the direction signify, like in the example of torque?
Yeah, the direction will signify something to do with the sense of the rotation imparted by that torque. So we will learn later on that a torque can cause some kind of rotational motion. And then the question is, does it rotate counterclockwise or clockwise? And that direction is related to that. Yeah, but I will say it in more detail when we talk about such things. But are you okay with at least this rough indication?
Yes, sir.
Okay. Yeah. You are
Abhishek.
So Abhishek, sorry. Abhishek, full name, please.
Abhishek Goyal.
Goyal. Okay. Yeah. I must admit that in my screen, I can only see like 5 names. And so I can't see who is speaking. I mean, I can't identify who is speaking immediately. So that's why I encourage you to tell me your name. And your full name is better than your half name, always. Okay, let us go to, okay, there's also a geometric quantity which is nicely captured by the cross product. So if you have a pair of vectors A and B, then you can construct a parallelogram spanned by A and B. So this is A and that is B. And by the parallelogram, I mean you draw this parallel line to B and to A, and they meet at the diagonally opposite corner. That's the parallelogram. And then the area of this parallelogram is of much interest in many contexts. And that area, you may recall, is given by AB sine of this angle. Yeah. So you will notice that that is equal to the cross product in magnitude. So the area of a parallelogram is given by the magnitude of the cross product. And in the case of the area, areas, if you regard it as just a positive number, then the order doesn't matter. Yeah. However, there are many contexts in which we want to regard the area itself as a vector. And in that case, we will be more specific and say that the area of the parallelogram spanned by A and B, A followed by B, is a third vector which points along the cross product. So that will be the area vector, which is A cross B. And that is not the same as B cross A. So that will that is a distinction we will find useful elsewhere. Yeah. Okay, any question right now?
Sir, from this, can we say that if A and B are in same direction or in opposite direction, they will not form a parallelogram, so they will not have any area.
You're
so
quite right.
Its magnitude is 0.
Yeah. So yeah, you're right. You're very right. I might say it in a slightly different way. I might say that they form a parallelogram, but that parallelogram has sort of collapsed. Yeah, it has no height. Yeah, So it forms a what might call you're right, they form a parallelogram of zero area. Yeah, so the case you are looking at is A and B collinear. So yeah, so the third vertex, if you add A and B, will also lie along the same line somewhere here. This is the vector A plus B. Yeah, remember the parallelogram rule of addition of vectors will tell you to come here. And it is clear that it doesn't enclose any non-zero area. So the word degenerate is often used for such situations where something collapses. Okay. Any other? Sorry, who asked that?
Srinish Shinde.
Srinish Shinde. Okay, great. Yeah. So now I wish to briefly mention some things about linear combinations and independence. These are things that already came up in a more informal way last time. So if we have vectors, we can talk about the linear combination. Given a pair of vectors u and v, and a pair of real numbers alpha and beta, we form a new vector using a combination of multiplication by scalars and addition of vectors. So we combine those two operations and form a new vector called alpha u plus beta v. That is called a linear combination. Okay, so this is called a linear combination of alpha of u and v. So the coefficients are real numbers here. So the vector space we are working with in this case is R3. It's a three-dimensional real vector space, and therefore the coefficients are real. Okay. Now, having this notion of linear combinations, one can talk about linear dependence slightly more precisely. So two vectors u and v are called linearly dependent if one can be expressed as a multiple of the other. Either one can be expressed as a multiple of the other. So geometrically, what this means is that they are linearly dependent if they point in the same direction or in opposite directions. Okay, so that's what it would mean for two vectors to be multiples of each other. Yeah. So if you have A this way and B that way, they point in the same direction, and we will say they are linearly dependent. And in that case, the one of the vectors, okay, let's call them u and v, u is alpha times v, or v is beta times u. Okay, so either one of these formulae must hold. Yeah. For some real numbers, alpha and beta. So either u is a rescaled version of v, or v is a rescaled version of u. If that is the case, we will say that they are linearly dependent. Now, why did I give both possibilities? It is to avoid some minor confusion. Yeah, and that is what I will clarify now. Okay, I'll come to that in a moment, but let me complete this remark about linear dependence. So when two vectors are linearly dependent, there is a linear combination, namely u minus alpha v coming from here, or v minus beta u coming from here, that vanishes. Okay, so we are developing this notion as we go. Yeah, we started with the geometric concept that if two vectors point in the same direction or opposite directions, then we consider them dependent. Then we abstracted from that an algebraic formula saying either u is alpha v or v is beta u. And then we applied another algebraic operation of taking it to the left side and found a linear relation among them, that u minus alpha v is 0 or v minus beta u is 0. So, so I hope you are following the process carefully. This is how we generally work. We start with some physical concept or geometric insight. From that, we abstract some formula, then we apply some algebraic operation on it, and then we get some fancy definition. Okay, so what is this? Let us just finish here. So, but you may wonder why I am taking both possibilities. It is to avoid some special cases. We need to allow for both the possibilities. That is either u is alpha v or v is beta u, because of some special case. Yeah, for instance, if u is 0 times v, okay, if u is 0 times v and v is not the 0 vector, so you have some vector v and u is 0 times v, so then u is the 0 vector. All right, u is the 0 vector. Then we can certainly express u as 0 times v. So we have such a formula, u is 0 times v, and we will say that they are linearly dependent. Yeah. And they satisfy a linear relation, namely u minus 0 times v is equal to 0. That relation does hold. However, the other relation unfortunately doesn't hold. We cannot express v as a multiple of u. Okay, I hope you see why. We cannot express v as a multiple of u. But from your intuition, can you tell me, if I want to force you to express v as a multiple of u, what would that coefficient be?
One by beta.
1 by beta indeed, but what is beta here?
Beta non-zero. When beta is non-zero, then
Yeah,
is
okay.
equal to 1.
If both the vectors are non-zero, you can of course go from this relation to that relation simply by dividing. Yeah. But the problem is over here, alpha is simply 0. So I mean, so in general, beta is 1 upon alpha. Okay, so when alpha is non-zero, beta is well defined. The problem is that here alpha itself is 0, so I cannot divide by it. But as Chandralekha Pari has said, in spirit you have to multiply by infinity. So okay, that's all I meant. So if you don't know how to divide by 0, then you throw up your arms and say, okay, there is no such relation. Okay. Yeah, so any question about that? The point is that there is no way of expressing v as a multiple of u, because u is the 0 vector. So we have to look for the other type of relation. Okay.
Even infinity will not also define the relation.
Yeah, we are a bit averse, allergic to infinity, so we don't include infinity as a real number. Yeah, sadly, yeah. But we avoid such allergic reactions and simply say there needs to be some linear relation among u and v. Some linear relation, this is fine. Yeah, u minus 0v is a linear relation.
Sir, is there any reason that we cannot simply say alpha u minus beta, alpha u plus beta v equal to 0?
Yeah,
Some alpha.
For some alpha beta, that is right, absolutely right. Yeah.
So why is it important to notice for u equal to alpha b or v equal to beta u? Why is that needed, like differently?
Okay, you have asked a question which is very relevant. It again goes into the process of discovery. You are starting from the end point. I'm starting from the starting point. I am starting from a physical intuition that two vectors are linearly dependent if one is a multiple of the other. I'm starting from that very basic geometric viewpoint.
Okay, sir.
Okay.
Okay, sir.
Whereas you are starting from the answer after a lot of thought. I am going to arrive at your answer through 3-4 steps. The point is that there may be no relation of the sort v is equal to beta u, but there may be a relation of the sort u equal to alpha v. Okay, so we should not be so adamant and say one should be a multiple of the other. All we really need is that a linear combination should vanish, namely some alpha u plus some beta v should be 0. Okay, so as you rightly pointed out, if this condition holds for some alpha beta, not
sir,
both.
one other thing, alpha beta should be not equal to 0.
Yes, you read my mind. If some such relation holds for alpha beta, not both 0, then we will say that u and v are linearly independent. Yeah. So the reason I introduce things this way is that thinking of u as alpha v is geometrically very simple. I mean, you think of a vector as some arrow and then another arrow, which is a rescaled version of this arrow. All right. So from that viewpoint, it is very intuitive. If you have coefficients for both of these, what does that mean? Well, you have to rescale both the vectors and add them up. If you're happy to think that way, you can certainly start that way. Okay, so yeah, so okay, so let me just complete this story here. But no, first, any questions from others?
So then in this case, zero vector is linearly dependent with each and every vector.
You are indeed right. The zero vector is linearly, or let me write it differently. 0 and any vector A are always linearly dependent. Yeah, and that is because the A vector can be expressed, sorry, the 0 vector can be expressed as a multiple of the A vector. Which multiple?
0 multiplied by 0.
Precisely, 0 times A. Okay, so a 0 vector is always linearly dependent with any other vector. You got that right. And who were you?
Sir, I was Kaustubh Manda.
Okay, you are Kaustubh Manda.
Yeah, I am.
Okay, all right. All right. So now let us proceed. Any other question? By the way, who told me about this linear combination?
Hello, sir. Yes.
Yes. Hello, but who are you?
I mean, linear combination alpha u plus beta v or 0 vector?
No, this alpha u plus beta v. Yeah, I'm just asking what your name is.
Ryan Hota.
Ryan Hota. Fine. Okay. Okay, so then I just make a remark connecting this linear dependence or independence with the cross product. So I leave it to you to check that u and v are linearly independent if and only if the cross product is non-zero. Okay, in fact, several of you have already essentially pointed this out. Yeah, if the cross product is non-zero, then they will enclose a non-zero area of the corresponding parallelogram, and consequently they would be linearly independent. Okay, so I hope that is clear. If u and v are linearly independent, then the area of the parallelogram is not equal to 0. Okay, so that is all we are saying.
Sir, maybe this question is irrelevant in some way, but could you please define a parallelogram? Like, what's the parallelogram you're taking?
Okay, yeah, our parallelogram is the following. You are given two vectors emanating from the same origin. Okay, so that is the data provided to you. Yeah, and I am supposed to parallel translate the v vector along the u vector to its tip and produce a parallel translated v vector. And then I'm supposed to do the same thing with the u vector, parallel transport it around v to this point. Yeah, and now we have now defined 4 line segments that forms your parallelogram, and the new vertex of that parallelogram is called the sum of the two vectors. Is that satisfactory?
So my question is that do the parallel vectors, when you apply the parallelogram law, two parallel vectors, does that form a parallelogram?
Sorry, we are defining a parallelogram for 2 vectors emanating from a common origin.
Yes. So two parallel vectors emanating from a common origin.
Oh, okay. You mean something like this?
V and 2v.
Okay, okay, fine. Yeah. No, so sure, they do form a parallelogram. It's a rather collapsed parallelogram. Yeah, this is some messy thing to draw, but yeah, I can try to draw it. tried it once before. I mean, the point is that you need to find the third vertex. So you have to take the sum of these two vectors. Yeah, and you know what that is. Both point in the same direction. So there's sum also points in the same direction. I will point and put it here. Yeah. Yeah. So the parallelogram that we are now defining has to have four vertices. They are the origin, this point where U ends, the point where V ends, and where the sum of them ends. Yeah, so we have defined 4 points in a plane. If you don't like it, that is your problem, but this is my parallelogram. Are you okay with this?
Yeah, thank you, sir. But I mean, like, I want to know where geometry and physics differs. That's
Okay. They don't differ too much. Yeah, we will see. But no, over here there is really no physics. I mean, there's not much physics, at least. The question is, why are you doing this? And that is for physical reasons, of course. But right now, we are simply
so where vectors is not actually physics, yes, sir.
Oh no, that's a good question. But a vector is a useful concept in talking about physics. All right. So if you want to talk about the displacement of a particle, then an enormously useful concept is a vector. All right. So this is the message of a couple of 100 years of careful thought. Yeah. So yeah. So if you want to model physical systems and their motion, you're kind of forced to invent the concept of a vector. If you want to talk about the force acting on a particle, after some thought, you find that it has some direction and then it also has some magnitude. So, okay, why not introduce some concept like a vector? Yeah. And if you want to talk about the position of a particle in some way, it is helpful to define some origin and some vector pointing that way. So concepts of vectors naturally come up when you want to discuss the physics of particle motion in our space. Is that okay?
Yes, sir. Yes, sir. Thank you, sir.
Okay. Okay, good. Was that Ryan Hota still or somebody else?
Yes. Yes, sir.
Okay. Yeah. I am trying to figure out your name from your, what is it? From your voice, but it's not easy. Okay. Okay, so then let us now go further in this business. As one of you already pointed out, the zero vector and any other vector view are always linearly dependent. Okay, and we already displayed a relation among them, linear relation. Yeah, okay. Now let us go further and talk about linear independence in a more general context, not necessarily on the plane or in three-dimensional space, but okay, we can be specific to three-dimensional space. That's a nice context to study. So let's have some vectors v1, v2, v3, and so on. We will say that they are linearly independent. Okay, and that intuitively for two vectors, you already know. What does it mean to be linearly independent? They form a parallelogram with non-zero area. They point in distinct directions. That is the physical or geometric idea. And now we want to give an algebraic statement of the same thing. Are said to be linearly independent if the only linear combination of them that vanishes is the one where the coefficients are all zero. Yeah. Okay, so this is a reasonable definition from our previous discussion. Yeah, I hope you will feel that way, that if you have two linearly independent vectors, yeah, like this u and v over here, the only way you can take some linear combination and get zero is to take the coefficients themselves to be zero. Okay, I hope that is intuitively or geometrically clear. If I multiply u by some non-zero constant, I will simply get another vector in this direction. If I multiply v by another non-zero coefficient, you will get some vector in this direction. There is no way I can add these two vectors and get the zero vector. The only way it's done is to make the coefficients themselves to be zero. Okay, so this is our second instance of going from algebra to geometry. We are going to now define vectors as being linearly independent as the case if the only linear combination that vanishes is the one where the coefficients are all 0. Okay. In other words, the only linear combination that vanishes is the trivial one. So when we say the trivial linear combination, we mean the combination with coefficients all 0. Is that definition palatable? If you're seeing it for the first time, I think it requires some thought and playing around. But any
Sir,
immediate question? Yeah.
Sir, how do we think about it geometrically? Like we have taken more than 2 vectors. So how do we think about it geometrically?
Okay. I would encourage you to do this in your spare time, or I'll do it later. But okay, I prefer to start with 2 vectors. Are you okay with 2 vectors, or your question is specifically to 3 vectors?
The 2 vectors is easy, like for 3 vectors or more.
Okay, so you are asking about 3 vectors. Okay, fine. Yeah. Okay, let me see if I can. But okay, rather than make a hash of this, okay, let us start with 2 vectors. Let's start with U and then V. Now tell me, are these linearly dependent or not?
These are linearly independent.
Independent, yeah. From the picture, it is clear. So, but now I'm adding a third vector to this collection. Now, so yeah, so okay, I think you will understand as we speak. There are various possibilities. Now, U and V span a plane. I think you will agree on that. U and V define a plane. Now, my third vector, if I choose the third vector in a certain way, then the combination, those 3 will be linearly dependent. So tell me what way I should choose the third vector W to get a linearly dependent set based on the
in the same plane.
Indeed, yeah. If W lies in the same plane, I mean, could point in any which way, could even be the 0 vector for that matter. Yeah, in any such way, the resulting set of 3 vectors U, V, and W are then linearly dependent. And what that would mean is that there is a non-trivial linear combination that is 0. Okay, are you with me?
Yes, sir.
That means I must offer to you a non-trivial linear combination of these 3 vectors, which is the 0 vector. Okay, and we will do that here. Of course, I can't put the numbers because I have not put these things very precisely, but I think you will agree with me that we can take some alpha U and some beta V, all right, to get my W. Okay, let me do this a little carefully. Suppose somebody gave you U and somebody gave you V and somebody gave you W. Yeah, I claim that there is always a parallelogram that you can form with sides collinear to U and V such that the third vertex is W. Okay, this is supposed to be a parallelogram. So I must rescale U appropriately. I must rescale V appropriately so that the sum alpha U plus beta V is equal to W. Okay, I claim this is always possible. I mean, from the picture, it is clear this is possible. And therefore, we have arrived at a non-trivial linear combination, namely alpha U plus beta V minus W equal to 0, where the coefficients are not all 0. Yeah, so through this example and your help, I have partly addressed your question, I hope.
Yes, sir, yes.
Okay, and if by mistake your W vector did not lie in this plane, pointed in some oblique direction, I don't mean orthogonal to the plane, just some oblique direction, then it will never be possible to take a linear combination, a non-trivial linear combination, and get 0. So I hope I have provided a little bit of intuition on this question. 3 vectors in a plane cannot be linearly independent. That is the message. Slightly more generally, in 3-dimensional space, namely R3, we can have at most 3 linearly independent vectors. Yeah, on the plane we can have at most 2 linearly independent vectors. In 3-dimensional space we can have at most 3. Okay, I hope you have some intuition for that. I mean, these things will be formally done for you in your linear algebra course. So I leave.
Sir,
Yeah.
I didn't get
Oh, please repeat your question.
I didn't get it. Means how it is.
Okay. Let's consider 3-dimensional space, the space around us in this room, right? And I ask how many vectors can be linearly independent. Okay, and I claim that you can have at most 3 linearly independent vectors. Is the statement clear to you? I mean, leave aside the argument why it is true. I'm not hearing you. Okay, let me give you an yes.
Sir, does that mean that in Rn we can have at most n linearly independent?
Yes, that is a
Like,
generalization.
generalization.
You are absolutely right. In Rn, you can have at most n linearly independent vectors. You're absolutely right. Yeah, and if you add a n plus first vector, then it will be possible always to get some non-trivial linear combination that vanishes. Yeah, so you are on the right track. Yeah, I mean, I don't intend to. I mean, I already indicated why this is true for R2. A generalization of that will work for R3. I hope.
Sir.
Yeah, I would like you to play around and see whether you can infer this for yourself. Okay. All right. Now it is 11:43. So I think we are practically at the end of our time. Do you have another course after this?
Yes.
Sir,
Okay.
English.
Okay, English. So I should wrap up then. So, okay, rather than start a new topic, I will ask you whether you have any question right now.
Sir, actually, to find out linear independence of 3 vectors, there was a trick taught to, which was that A, B, C are 3 vectors. A dot bracketed B cross A dot B cross C.
Yeah.
Is this correct?
Box product.
You're right.
Box
Yeah.
product.
Yeah, you have given a nice idea, and now I should of course say that the idea you have mentioned is a generalization of the idea we already used in 2 dimensions, right? No, I'm interpreting geometrically what you said. We said that 2 vectors are linearly independent if and only if the cross product is non-zero. Yeah, and what is that saying? It is saying that the 2 vectors span a parallelogram of non-zero area. Similarly, in 3 dimensions, if you have 3 vectors, you can ask about the parallelepiped that they span. All right, and that is a funny figure which you can draw. I will attempt to draw it. Yeah, so you're supposed to draw a parallelogram and then extend it to the 3rd direction. Okay, I'm not.
Sir,
Yeah.
is the box product the area of the volume of the parallelepiped?
Exactly. That quantity which you said, A dot B cross C, is the volume of the parallelepiped. Yeah, so you have generalized the concept of area of a parallelogram to the volume of a parallelepiped, and if that volume is non-zero, then the three vectors are linearly independent. So nice idea. Who was that?
Sir, I am Nirjana.
Nirjana. Okay, yeah. So thanks for pointing that out. We will talk more about this scale. This is called, I thought you called it the box product. I call it the scalar triple product. Yeah, but if you like geometry more, simply call it the volume of the parallelepiped. Yeah. Okay, any other question right now? Okay, if not, I thank you for coming for this second meeting. We shall reconvene next Tuesday. Have a good day, and I will communicate anything through email and on the website. All right. Goodbye then.
Sir, is there any homework to do over the weekend?
I will communicate that to you. Yes. Yes.
Yes.
Sir, will it be via Moodle?
Sorry. Will it be?
Sir, will it be via Moodle or email?
Yes, yes. Homeworks are all submitted through Moodle. Yeah. But the announcement I will send through email. Yeah, and the instructions will be there. Yeah, is that okay? Any further question?
Okay, sir. Okay, sir.
All right. All right. Thank you.
Sorry, sir, I was evicted for a little bit. Can you please repeat whether you said anything about the homework?
Yeah, I will communicate the instructions regarding the homework as well as the problems through email, and it will also be posted on the website. But you will hear from me through email.
Thank you, sir.
Okay.